In this problem, we are asked how many squares are in a 200 by 200 grid. So it's a grid that goes 200 by 200, which is huge. Each side has 200 units, so there are a bunch of little squares. 200 times 200 is 40,000 little tiny squares in such a grid. However, that's just the tiny squares. There will be larger squares still, so there will be a whole lot of squares inside a 200 by 200 grid. And we have no clue how to tackle a problem as big as that. But we do have some nice tools at our disposal. And what we're going to do is go into Desmos and create a table. And we'll actually make a table of values. So for our table of values, we know that if we have a 1 by 1 square, we'll end up with, or a 1 by 1 grid is 1 square. What happens if we up it to a 2 by 2 grid? And in that case, I count 4 little squares and 1 bigger square for a grand total of 5. Okay, what if we had a 3 by 3 grid? Count 9 little squares. I count 4 2 by 2 squares. Be careful to count them all. And 1 3 by 3 square. We add those up, we'll come up with 14 squares. Okay. Getting a little trickier. We've got a 4 by 4 grid. In that case, there are 16 little squares. There are 9 2 by 2 squares, 4 3 by 3 squares, and 1 4 by 4 square. That adds up to be 30. Already it's getting pretty tricky. You gotta make sure we are careful accountants to get the count right. And then as we look at a 5 by 5 grid, so we have all the squares we had before, but we'll end up with 25 new squares. It'll work out to be 55. Okay, so that gives us a good starting point, but we don't want to continue this way to get up to a 200 by 200 grid. So we are going to try to fit a curve to these numbers. And we're going to use the Desmos curve fitting. So we will write y1. We use the tilde. So y1 is approximated by, and we're hoping it's just some nice polynomial. Now, we're not so optimistic as to think it'll be just maybe x to the 5th power, or something clean, but we're going to throw in a guess. So if we add up a bunch of squares, maybe we will end up with a polynomial of degree 3-ish. So I'm going to type in a times x1 cubed plus b times x2 squared plus c times x3 plus d. So it's some combination of a cubic polynomial, a square, a linear, and a constant polynomial. When we throw that in there, it gives us a curve with various parameters here. Why did I use x1 and x2? X1 was the only variable we had. Okay. When we do, it gives us values for a, b, and c. So if I were to try to give a formula for this function, I would write f of x equals, so the a was 0.333. That looks to me like an approximation of 1/3. 1/3 x cubed plus 1/2 x, because the b was 0.5. C was 0.167. I'm guessing that's an approximation for 1/6. Oh, I forgot my exponent. 1/2 x squared plus 1/6 x. And this 4.6 times 10 to the negative 15th is d. And that's within rounding distance of 0. So we're going to assume that that point was not included. Alright, so I'm going to jump up here So if we look at our curve, we are hoping that it hits the same points. So up here, I'm going to type f of x1 in my rightmost column. And, ooh, we see that it does give the same outputs. So, could hide the grid for the moment and just look at the curve. It does look like it goes through the points that it's supposed to go to. And not only that, but we can continue adding values. Ho ho ho! Look at that. A 9 by 9 grid would have 285 squares inside it of various sizes. And at this point, we're ready to actually go back and answer the question. We've come up with a beautiful model. We have our function f of x. So, how many squares are in an x by x grid? Well, that answer is given by f of x here. So the number of squares in a 200 by 200 grid will be f of 200. Whoa, 2,686,700 squares.